All right, now this is working. Yeah, it's on the left-hand side you have solid. On the right-hand side you have what? And now, how much ions do you have? Well, we could have a unsaturated solution, right? A saturated solution or a supersaturated solution. So what is it going to equilibrate with? You know, the solid equilibrates with water to form a saturated solution. And so that's what's happening. And so the answer is true.
It should be false.
Oh, unsaturated, it says unsaturated? Then the answer should be false because it means that the concentrations should increase. Unsaturated means QSP is less than KSP and it's got to shift to the right. To the right. Okay, any other questions? Sorry.
Yeah, 13. It says circle the possible species in saturated solution of lead iodide. And then I have, I'm not sure on the answers. I mean, I have some that I think it says circle all, but then
Okay, what are the choices? The first choice.
you have lead ion, iodide ion, and then PBI, and then PBI plus, and PBI2 aqueous.
So we have lead ion. This is lead 2 iodide?
Yes.
Normally we go to lead 2 plus 2 iodide. This is normal KSP, right? And so what are the choices here? Lead ion?
Yes.
Lead 2 ion?
Yes.
What else? Iodide ion?
PBI.
PBI plus?
No, PBI and PBI plus.
PBI like this?
Yes.
All right.
And PBI plus.
PBI plus?
PBI2 aqueous.
PBI2 aqueous. And the question is,
Circle the possible species in a saturated solution.
circle the possible species in a saturated solution. So normally we would do, actually there's some glare off the board here. Can you guys see the board okay? Yeah. Let's focus. Over that door. So who answered this one? Who would you guys got? One light's missing there. Obviously, this, right? This should be easy. PB2 plus. Iodine. That's it? That's it for ideal solution, right? But do you guys know about non-ideal solutions? Tell me what you know about non-ideal solutions? Ion pairing. Right. Ion pairing can occur in non-ideal solution. So what else might be possible? This is kind of basic knowledge here. This would be more advanced. So, they'd expect the sharper students to be able to go, probably this, because ion pairing. Not necessarily sharper, just people who are familiar with ion pairing, right? Non-ideal. And potentially, this, if the two, you get a cluster, PB2 plus, 2 iodides come. They pair. Are these permanent? No, I mean, they'll dissociate. And so this, and so 1, 2, 3, 4. Right. This is impossible. Why? Charge dumbbell. Yeah. And so if you go back to chapter, what chapter was that? In my book today. If you go back to chapter 13 and read that 2 pages back there, then you might. You got to figure there's going to be some ion pairing. There could be other species as well, clusters of species too. And so these are potential species, not necessarily that they're going to occur. And so this particular question, I scaled the grading on this, depending on how people answered it. I think I don't know if I gave bonus. I don't remember in this one, But for sure A and B. That's the bulk of the points there. Okay, what else?
This one is, which one has a higher solubility, silver chloride or what's that? Silver chromate.
Yeah, just silver chromate.
Yeah, silver chromate. And then they give us the KSP values. So I'm thinking when they're really close, I know that even the one that has the smallest KSP can be the one that's less soluble. How can we tell when because if they're separate, like they're very different, the KSP values are far away from each other, we can tell, but when they're super close. So it is a solubility?
Yeah, you have to do that because the trick here is S can be the square root of the KSP, the cube root of the KSP, the 4th root of the KSP, the 5th root. It's nonlinear. You can't think linearly just because one KSP is bigger than the other or smaller than the other, right? And so this was the point I was trying to make about that. Don't be careful of comparing the KSPs directly because if KSP was always the square root, then compare them, but it's not. And so it's tricky. It's a trick question. It's a trick question because the species with the smaller KSP could potentially have a larger solubility. That happens. And so you got to be careful about that. So this we talked about. Elevate my leg.
For what?
All right. Other questions? So you have to do the actual calculation. You can't just compare the numbers. All right. What else? You guys have questions?
So the silver chloride should be most soluble in water. Only the sodium.
I think so. She's asking silver chloride should be most soluble in water, potassium chloride, or sodium nitrate.
Okay. Well, this, I'll tell you. This is why when I was a student, I like to look at a lot of different books because there are certain things that I like. There's certain problems that you go, wow, that seems like a very hard problem. But if you see somebody and solve it, or if you go through how it's done, then you go, oh, maybe that wasn't as hard as I originally thought. And so oftentimes, what I found as a student is the challenging problems would come from the next course, And so what I would do as a student was not only look at our textbook, but I'd look at a more advanced textbook, right? In the more advanced textbook, what happens is they take one specific topic and then dig into it a lot deeper. Right? And so you get a really challenging problem in your course, but it turns out, it's a basic problem in the next course, right? And then you go through and you see how it's solved, and then it makes it easy, right? Well, this particular problem, I skipped entirely because I don't know why. I must have forgotten about it. There's the common ion effect, and there's something called the uncommon ion effect. The uncommon ion effect is related to ion pairing. And so the uncommon ion is, this would be more soluble in sodium nitrate. Why? If I had aqueous sodium nitrate, well, you think sodium nitrate doesn't participate in this at all, but it does. How would sodium nitrate participate in this?
Ion pairing.
Ion pairing. And so what happens is we call this the free ion. If you take the free ion and then all of a sudden we surround that free ion with nitrates, then essentially we're doing a Le Chatelier shift, because we're decreasing the concentration of free ion, because having these nitrates surrounding this is going to mean this is less likely to precipitate or crystallize in the reverse direction, right? It hinders this. And so what we have is a mild ion pairing effect, actually not necessarily mild, because this is a 2+, this is 1-. Well, this is kind of a big ion compared to, well, iodine's a big ion too. And so we get ion pairing effects here. You see that? And those ion pairing effects can really shift it this way. Because now, in order for the free ion to react with iodide, we have to break it away from the nitrates, and then it can react with the iodide. All right, this is something I talked about in Chem 1A, and you might have heard about it in your Chem 1A class. The reason why HF is such a weak acid. You know, the reason why HF is such a weak acid is because of ion pairing, right? And what happens is you don't have free hydronium, because that's paired with the fluoride. And so in order for the hydronium to react, or the H+ to react, right? I'll just say H+ to react, it has to break away from the fluoride first. And because of the strong ion pairing there, that costs you energy. And so it's much less reactive as an acid in aqueous solution than HCl, HBr, and HI. And so ion pairing first appeared in Chem 1A, and this is non-ideal. It's like gases. You know, gases, what makes them non-ideal? One of the things that makes them non-ideal is intermolecular attractions. You know, they don't behave as independent particles. In kinetic molecular theory, they should be totally independent particles. But if the two water molecules are kind of attracted to each other, and there's, you know, hydrogen bonding interaction there, then they aren't going to act independently. And it's going to decrease the pressure. And so the same kind of concept, but we see it in solutions, right, rather than in gas phase. And so that's that. And so this is called the uncommon ion effect. The uncommon ion effect causes ion pairing to occur, which subsequently will increase the solubility. Is it a significant effect? No, it's a very minor effect. You know, in fact, we don't. You could do the calculations for this. You could, but we don't even factor it. We just know that there's potential. And so here, water, it should be more soluble in sodium nitrate than in water. All right, so what were the choices that we had?
Water, potassium chloride.
Okay, potassium chloride would be called the common ion effect. The common ion effect is significant. Having a lot of common ion there is like the remember predator-prey thing we talked about so many times. That type of thing. And so for sure that would decrease the solubility of it. All right, what else?
Okay, this one is just to make sure. 16 says, calculate the solubility of calcium sulfate at a pH of 3.00. That hydronium is going to be initial, right?
At a pH. At a pH of 3. No, that hydronium would be final equilibrium, because it's at that pH. What is the solubility at that particular pH? And so that hydronium should be the final hydronium.
We did an example in class, and we had it as initial. So now, like, when do we?
It would be, if I said in a pH 4
Okay.
solution, then that would be initial.
So this one would be final because
Yeah,
it's at that.
because, okay, you calculate the solubility using that as your initial. The solubility you're going to get is going to be at a different pH, because the hydronium is going to change. If the initial hydronium was pH 4, some of the hydronium is going to be consumed or produced, and the pH is going to change. And so the actual solubility that you're calculating is going to have a different hydronium than pH 4, or whatever it was. Does that make sense?
Yeah, so this is, okay, this one is at the pH. That would make it a final
Right, that would have to make it a final.
in a pH solution.
Yeah, in a pH 4, then you're saying, well, even in a pH 4, that's ambiguous. But at for sure should be final.
At.
You know, but what we'll do on the test is, you know, I'm just going to tell you with an initial pH of this or with a final pH of that. How about that?
Okay.
Because I don't want to get into, see people, half the people do it one way and half the people do it the other way. So we'll just make it very clear for the test.
So
Okay.
what the pH.
Yeah.
And then for 17, basically we're doing a fractional precipitation, and I was able to do that. But then the last part of the problem says calculate the percent precipitation and percent remaining of these ions. So I was confused, like what ion you were referring
I said it, I gave you the parameters for that?
to. Yeah.
Okay. The percent, you have to figure out which one precipitates first.
Yeah, and then, but would it be silver that we're looking at or chloride? Because silver chloride precipitated first.
Well, what ions are you trying to separate?
We're trying to separate chloride and chromate.
Chloride and chromate. So then it would be related to chloride and chromate. And so what you would do is, if you figure out first which one precipitates first.
I did that.
Okay, chloride.
Yes.
And then you'd figure out, well, how much chloride remains when the chromate is saturated. That is, how much chloride remains once the chromate will start to precipitate. And then figure out the percent chloride remaining and then percent precipitation of chloride. The chromate should not precipitate in an ideal fractional precipitation. And so hopefully the percent chromate precipitation is 0% chromate precipitation. And hopefully 100% of the chromate remains in solution.
So when we do the percent precipitation, do we look at the initial chloride and the final chloride?
Yeah. Yeah. But the way I do it is I do it by calculating the percent chloride remaining. That is, the final chloride divided by the initial chloride times 100%. That's the percent chloride remaining. And then 100% minus that gives us the percent precipitation. I do not subtract. I do not subtract. The reason I don't subtract it is because the numbers can get very small, and you can have round off error. That is, you know, I don't subtract it because what can potentially happen is you get 99.99999 whatever percent precipitation, which the calculator rounds to 100% precipitation, which is not right. And so I always go from percent remaining to percent precipitation to avoid that round off there.
Do you mind maybe doing that part? Because the thing is, like when I did by chloride, I still got like 100%.
You got 100%? You shouldn't get 100%.
Yeah, so
I know lots of people get 100%
Yeah,
because sometimes I pick the problem to see, you know, if they get 100%, are they going to go back and fix it, or are they just going to leave it at 100%? Lots of people just leave it at 100% because they don't want to hassle with it. But I'll give a little extra points to the people who don't, you know.
That's what I did. I mean, I still got 100%. I was gonna do
Well, the thing, you know, there's ways to make this problem complicated. You probably saw in the book. You know, one thing is I can have the initial concentrations different. The KSPs are different. If I have the initial concentrations different, You know, it's very easy to predict the wrong ion precipitating first, you know. And so we always calculate, what do we always calculate? We always calculate the no, we don't. I never calculate QSP. Never calculate QSP for fractional precipitation. But lots of people do. I see it on the tests all the time. All the time. You know, I see people going in circles a lot too. But we don't have to calculate QSP, you know. Right now the QSP would be 0 because we have no silver.
So we're calculating how many silver to be separated.
Yes. And so what did I call that? It's a very simple calculation 1. What was it? No solution dilution. Yeah. We are for these fractional precipitations. We're avoiding solution dilution because unless if I add solution dilution, that makes it 1 level harder or 2 levels harder. And so if you look at the fractional precipitation, I don't know. Did I work out an example? The example we ignored solution dilution completely.
Don't we do like QSP is greater than KSP?
No, I mean in a way yes, but I didn't. You know, I talked about that as just background for the calculation. If you go back through that, if you go back through your notes and you look, okay, what's really important here, and if you look through it, you know, once, twice, 3 times, then you'll see, oh yeah, there are basically just 4 calculations. What are the 4 calculations?
Concentration of silver.
5 calculations. Yeah. Concentration of silver required for what?
Saturation.
Yeah, or, you know, concentration of silver required to, and I wrote it like this, I hope, because I always write it, required to,
That's not
To separate.
but we did a pH, right? And so I said pH required to precipitate magnesium hydroxide. What did we do? Magnesium hydroxide and iron. So I said, what is the pH required to precipitate the magnesium? What is the pH required to precipitate the iron? That's a standard. Those are the first 2 calculations you do. You're trying to separate 2 ions. Fortunately, only 2. I don't want to give you like 5 or 6 ions, but you'd have to do it for each ion if there are 5 or 6 ions in there, right?
But then we didn't using the QSP is greater than or equal to KSP.
You're right. Right, but we called it what? We called it the pH required to precipitate. And so here we're just saying concentration of silver required to precipitate chloride. It doesn't matter which one you do first. How do you figure that out?
I use QSP
Yeah, okay. We want QSP to be
greater than or equal to KSP.
greater than KSP.
You have silver, concentration of silver and chloride greater than or equal to a KSP, and then sulfur. How much silver you would need.
Right, okay, so we'll have the silver ion concentration times the chloride ion concentration, right?
Yeah.
This should be greater than KSP.
Greater or equal to.
And so, yeah, greater than or equal. Well, equal to, we'll just saturate it. And so silver ion concentration should be greater than or equal to KSP over chloride. I don't call it a QSP calculation because in a typical QSP calculation, you're given the initials, right? In a typical QSP calculation, you want the initial silver and you want the initial chloride and see how does it compare to KSP. And so this is why I call it different. I call it, you know, the concentration required or the amount required to precipitate. And so we need at least this much to saturate it and more than this much to precipitate it. And so what does that mean for this? Well, what is that number? Somebody just tell me.
1.8 times 10 to the negative 9.
what was the chloride concentration?
0.100,
And the chromate?
0.100.
Oh, so they're the same. You know, in the book we'll have, sometimes they'll put a different 0.050, 0.100. That changes the amounts. And when you have that, the solubility depends on how much you have and the KSP and how it ionizes. You've got to factor all those in. All right, what's calculation 2? This is what you do. What you do is, okay, you take this. This is what scientists do. Scientists take a lot of information, right? It's not organized. And what they do is they do a process called data reduction. Have you ever heard of data reduction? You got tons and tons of data, and it's just too much to understand. So what you try to do is you try to look for patterns, right? Look at that table there. I try to tell you data reduction, and you look at that chart there, and that's a lot of data, right? And so most people look at that chart, well, that's a lot of data, and then forget about it because it's too much data, too much stuff to think about, right? And so what you as a scientist should do is you look through and you go through that chart multiple times, right? And then as you go through it multiple times, you start to see patterns in it. It might take many, many times, but eventually you'll see some patterns in there. Well, the same thing, I don't want to spell everything out for you because a great part of learning is finding these things and then you remember them. Because if somebody just told you, memorize this, memorize step 1, memorize step 2, then I found that doesn't really stay, And so I think for me, and this is why I say go through the notes multiple times so that you can go back and you can go, okay, this is, the first step I'm going to do. I'm going to figure out this. And then the second step to do is what?
The second precipitation.
Yeah.
Chromate.
So for chromate, we do the same thing. And so here, chromate ionizes a bit differently. See, I don't even have to write QSP here. I just say, okay, in order to figure out the silver ion concentration, it's got to be greater than or equal to KSP divided by the chromate. And so what does it count to?
3.3 sub 1 times 10 to the negative
Times 10 to the negative
6.
6. Okay. And so which one precipitates out first?
Silver chloride.
Yeah, silver chloride is going to precipitate out first. And so all this calculation does is tells us which one precipitates first. And where to stop adding silver. And so here, chloride, this precipitates first, and we better stop adding silver at what concentration? Yeah, okay, so we must stop when silver concentration hits 3.31 times 10 to the minus 6 molar. If we exceed that, what will happen? Both will precipitate. And so at this silver concentration, this is the next calculation, right? At this silver concentration, what do we do? We calculate the amount of chloride that remains. And so the chloride remaining how do I do that?
Final concentration over initial times 100%.
Don't have to
No,
find
not
the final chloride concentration is at the
Did you do an ice
We don't need to do nice. What's happening is the silver is going up. As the silver is going up, the chloride is going down. And so we got to figure out what the chloride drops to at this point.
So
How do we do it?
Find the new We have to find the new chloride concentration
Yeah, we find the new
And
chloride
silver.
concentration by doing what?
by using the KSP equals to
Yeah.
silver
KSP
chloride.
for ATC, right?
Oh, I see. I see, right.
This is the amount of chloride that can be maintained with this much silver ion, right?
My confusion was, I used 1.8 times 10 to the negative 9 instead of, like I used the silver like that.
Lots of people do that. I'll tell you, I see this all the time. People use 1.8 times 10 to the minus 9.
Yeah, why would that do
You get point. No wonder you're getting
100%.
100% because you're not going to precipitate anything. At 1.8 times 10 to the minus 9, the chloride and silver are saturated. Nothing precipitates. And you weren't calculating the percent precipitation. You were calculating the percent remaining. You get 100% remaining at this concentration. Is this enough, or do you want me to finish it? How about anybody else? So what you would do here is you calculate this. This is the chloride, the final, and then you take the chloride final over the chloride initial, and that's the percent, right? And so 4, we'll just calculate the percentages. The chloride remaining is this final chloride over the initial chloride, that's 100%. What's this number? Does somebody have it? 5.4 times 10 to the negative 5. And so we got 5.4 times 10 to the negative 5. I'd like one more digit here, though. Round off. And so on the test, show me one more digit. Divided by the initial 0.100 times 100% gives us
It would be 5. The other digit.
if the other digit would be 5.
Not
0.054. One more digit. 5. Yeah. Percent, which means the percent precipitation, 99.9455.
And then you'd ask if it's a complete precipitation.
Is that a complete precipitation?
Yes.
Yeah. Complete. So all it has to be is greater than 99.9%. So if you do some of these, even if you just do one of these, you should break it down, into, what am I doing here? You should ask yourself the question, what is he doing here? And if it doesn't make sense, you got to make sure it makes sense by the time the test comes. And then you want to break it down into a way that you understand. That's the best. Because lots of places you can make simple mistakes, in this chapter. This is the reason why this chapter is challenging, is because there are a lot of places where one can make a mistake. Okay, other questions?
I have one more.
Okay.
When equal volumes of 9, this is number 7.
Okay.
When equal volumes of 9.0 times 10 to the negative 9 molarity silver nitrate and 0.026 molarity chloride solutions are mixed, will precipitation of silver chloride occur? And then I put no.
Okay.
But like my reasoning, like I'm not like confident.
Well, tell me what you see in this problem.
I was thinking about like the molarities, like one molarity was very small, like
Okay, do you have to do the solution dilution first? Yes. If equal volumes are mixed, then it's a 1-to-2 dilution. And so every concentration needs to be chopped in half. You see? When you take two equal volumes and mix them together, then you just double the volume. And so one of the trick things about this question is solution dilution is required here. Whenever you mix two solutions, solution dilution is required. In fractional precipitation, solution dilution is not required, otherwise it becomes too much of a headache, right, to do. And so normally what we do in a case like this is try to add solid silver nitrate to avoid solution dilution, right? That's what we do. Otherwise, if you have to factor in solution dilution, it becomes quite complex. And so number one, on that particular problem, solution dilution is required. Anytime you add two solutions, you got to do it. And so in that particular problem, it might be, I don't know, even with solution dilution or without solution dilution, I don't know if you get the same result, you know. Usually I would try to do something like this. You know, without solution dilution, you get the wrong answer. With solution dilution, you get the right answer. But sometimes I'll just say, with or without solution dilution, you'll get the right answer. Okay. Just see.
It's different if you do solution.
It's different if you do. You see that? You got to be careful, because if you didn't do solution dilution, you get the wrong answer. It's just a QSP. A solution dilution is, I don't tell you the volumes, but you know, you don't need to know the volume because of the solution dilution equation. We'll call this V1 plus, this is the same volume, so we'll call it V1. And so we have the two. What's the concentration of the first one?
Silver nitrate is 9.9 times 10 to the negative 9.
And the other one?
Chloride is 0.026.
And so when we do this, we're going to get a volume of 2V1. And so then we just do the solution dilution equation for both. You know, the new concentration of silver nitrate is the initial volume, V1, divided by the final volume, 2V1, times initial concentration, 9.0 times 10 to the minus 9. V1 cancels, this is 1/2. This is going to be 4.5 times 10 to the minus 9 molar. Chloride, same thing. You know, it's going to be 0.013. And then just calculate QSP.
This here.
That's what you do in this particular thing. All right, what else do you guys have questions?
That's it for me.
Anybody else?
Fractional precipitation, what is the counter that precipitates first most of the coming down? Is it KSP, initial concentration, or final? Or not?
Normally, when we're thinking about, you know, fractional precipitation, if we look at the KSP values, you got to be especially careful, because normally, if we had which cation precipitates first? So let's say we had magnesium and iron 3 plus, and we're precipitating out the hydroxide, right? Well, iron 3 hydroxide is so insoluble. You know, the KSP is so small. Let's pick two that are closer. Let's do magnesium 2 plus and some other one. Let me find it. Appendix D. Let's precipitate out the hydroxide. 1.8 times 10 minus 11. You know, that's a tough question to answer because it depends on, you know, all the factors. What is the initial concentration? And so, for example, you would expect iron 3 to be less soluble. But if we had a higher concentration, let's say the magnesium is 0.500 and the iron 3 is 0.0100, then you're not so sure anymore. Because now we have a much higher concentration of magnesium than iron 3, so even though we expect iron 3 to be less soluble, well, it is less soluble, but you have a lot of common ion here, you have a lot less common ion here. And so that's going to affect its solubility, change it. And so, you know, it's a tough question to answer because you can't just look at this one factor, but you also have to look at the KSP value and you also have to look at how it splits. And so the easiest thing to do is just don't even think about it and just calculate it. You know, that goes for any fractional precipitation. I never guess which one's going to precipitate first. I always do calculation 1 and calculation 2, you know, and then I don't have to worry about it. A lot of people do guess. You know, they'll just automatically assume this species will precipitate first, and it's wrong. They get the wrong species. And so, you know, when they do the calculation, if you mess up the first part, the whole thing is messed up. So I still give partial credit, you know, if they do the rest of it correctly, they'll get some partial credit. But yeah, it's best not to guess. Just
What would be the
calculate.
most accurate answer? Because that's one of the questions on the practice.
Yeah.
Would it be KSP and initial concentration?
Okay, what were the choices?
KSP, initial concentration, final concentration, or none.
It says to circle
Okay.
all the five.
Circle all the five. I put A. The KSP and the initial concentration.
Which are most important? Okay, KSP for sure is important. Initial concentration, and final concentration doesn't matter at all. Final concentration. And so just A and B.
It depends on each two.
But which one is more important? You know, that one is difficult to answer. So I was thinking which one's most significant. All right, other questions on this? No? Good. There's something else coming up. Well, let's go back to chapter 14. We have to finish that hydrogen peroxide problem, I think. The decomposition of hydrogen peroxide. So, did somebody double check all the calculations for that? Yes? All right, the reason why is because the reason why I wanted you to double check is because in your book they do I got the data from the book and they graph it. When they graph it, it's not linear. It's actually and so what happened was we must have either did a calculation error or it must have been what? Yeah, just these random errors. Unfortunately, that's the problem with only using 3 data points. This is why in experiments we try to collect a lot of data, you know, to minimize the random error. And so probably what we need to do in this instance is be a little bit more careful and then either spread it apart, right? Let's take a look at this. You know, if I have 3 data points that are clustered together, it always looks kind of linear. But you know, as we spread things out over time, then we're going to see it's going to be quite nonlinear or quite linear. And did I already talk about this? So random error is experimental error. In the experimental error, you're going to have small fluctuations, you know, in the value. This is like pH. As you're reading the pHs in the titration, you expect some fluctuations there, right? Small fluctuation. But a small fluctuation here at the beginning results in a huge error. But a small fluctuation here near the end would result in a small error because these are so dramatically different, right? And so let's pick some points that are more spread out, or let's pick a 4th data point. What should we do? Yeah, okay. And then see how the results are. And so spreading out the points here, let's redo the problem here with the hydrogen peroxide. One of the clues, was there a clue that, we might be subject to quite a bit of error? Was there some kind of clue in that you saw? One of the clues that sent up a warning sign was it's either 0 or first order, but I don't have very high confidence in assigning this because the percentages for both of them were relatively high. They both had high error, right? If they both had high error, how can you really have confidence in one over the other because both are bad? And so let's see if we could get something a little bit better as far as the data goes in class. So let's do the 0 to 200, and then I'm going to go from to jump 0 to 200, and then we'll jump to 600. How about that? We'll take, let's say if I had 3 data points like this. 0 to 200, so we'll do the same. This will save us some calculations. 2.32 is that? And this one was 2.01. Is that right?
Yeah.
And then if we jump to 600, you know, we have a 1.49. And so a bit bigger interval here. All right, then we already know what the K is for this. And so let's go ahead and take the Ln concentration and 1 over the concentration here. And so what was the Ln of 232? This is just from last time. .841. 5. Okay, and then the inverse. 14310. And then 201 was what?
0.6981.
6981. And over here? Actually, you know, do I need to do this? You know, I don't need to do this. I do this for slope analysis. You know, but for K analysis, I don't bother with this. But you go, well, K and the slope are the same thing, aren't they? Yes, but they're calculated differently, you know? And so this saves me time. Because all I do is I just take the original data like this. and then figure out the K. And so for zero order, I'm going to call this first jump Ka and the second jump Kb. So I'll have a Ka. This is not acid, and this is not base. It's just the first one and the second one. And so for zero order, Ka is the slope. Well, what we do is we rearrange that equation. So it's the final minus the initial divided by t, and then a negative sign here. And so this should be the same as before. What was the slope before?
One
1.00155. Thanks. Okay, the units here are interesting. It's going to be molar per seconds or minutes? Seconds, thanks. All right, Kb. Okay, this we'll do here. Kb is going to be the final is 149 minus initials 201 divided by the time interval. The time interval is going to be 400 seconds in this case. We'll take the negative and make this positive because K is a positive. And so this will be what? 0.00013 molar per second. Thanks. Okay, now we go to first order. We go to first order. Ka is going to equal the ln of the final over the initial divided by t, and we'll take the negative of that. And so this is going to be negative ln of the final. Well, the final is 2. Actually, we already did this calculation, right? And so what was it? Ka. 0.0000017. 717. Okay. 0000717. What are the units here? Yes. Seconds to the minus 1. Now, where do the units come from? The units come from the equation, the rate law. Because in a zero order, the rate is equal to K, whatever, A to the 0. In this case, it would be hydrogen peroxide to the 0. And that would just equal K. Rates are always going to be molar per time. And so the K has to be molar per time. Whereas in a first order rate is equal to K, this to the first. And so the hydrogen peroxide concentration is going to be in molar. And so K must be per second. And so we have molar per second for the rate. The two rates are the same units here. The units are going to be molar per second. The units here are molar per second. Now Kb, we'll just go ahead and calculate. ln 149 over 201 divided by t. The time interval here is 400 seconds. And this gives us what? 0.0000000 748 seconds to the minus 1. Okay, then finally we should just check second order again. Check second order. Ka, just rearranging the equation, is 1 over the final minus 1 over the initial divided by t. And so we already did this one. What was it again?
0.000
0.000
332.
332. What are the units here? Yeah, molar minus 1 seconds minus 1. And the reason is because the rate law. The rate law we have is equal to K times the hydrogen peroxide squared. And so we're going to have molar squared per second. Then so we need to get rid of one of the molar because there's no such thing as molar squared, and the units are going to come out molar per second the same. And so K will have different units depending on the order. And it's going to be the overall order of the reaction. So if the overall order of the reaction was third order overall, then K would be molar to the minus 2, per second. And so if there are more terms here, you know, we just got to make sure dimensional analysis, they all cancel out to give us this. All right, KB, we calculate like this. It's going to just be 1 over 149 minus 1 over 201 divided by the time interval of 400 seconds. 0.00034. 434. I can bring my calculator today, but let's calculate the percent difference. What is the percent difference between these two?
30.7.
30.7%. Okay, let's go to first order. What's the percent difference here?
4.3.
4.3%. And the percent difference here? 19%. Okay. 4.3% is still kind of high, you know, but it could be due to the errors, random errors, fluctuations. But now look at the zero order. As we spread out the data, they're starting to deviate more and more. See? And so clearly it looks to be first order. Actually, I'm going to leave this table here. So first order must be it. And so then that means the rate is equal to K H2O2 to the first. Now, what K value do we want to use? What we use is the average K. And so this would be K average. K average is going to equal Ka plus Kb because the two Ks are supposed to be the same. K is a constant divided by 2 or however many you have. And so the average K is going to be 0.000. What? 733 seconds to the minus 1. And so the rate law looks like this. The rate is equal to 0.000733 seconds to the minus 1 times the molarity of the hydrogen peroxide. And so we could figure out the rate at any concentration of hydrogen peroxide. What would the rate be at this concentration of hydroxide? What would happen if we doubled it? Well, if we doubled it, the rate should double. You know, triple it should triple. And so with this, the rate law, we can calculate the rate at any concentration. All right, if we have the rate law, we also want to get the integrated rate law. Now, the integrated rate, we can get that based on, this is a one reactant reaction. And so the integrated rate law is going to look like this. It's first order, so it's going to be ln, ln hydrogen peroxide at time t over hydrogen peroxide initial, 0, divided by, is equal to minus K T. Well, we know what K is. K is minus 0.000733 seconds to the minus 1 times T. So we want this. This is the integrated rate law. And so we could ask ourselves, you know, how long would it take 99.9% of the hydrogen peroxide to decompose? So how long would it take 99.9% of the H2O2 to decompose. And so if we want 99.9%, that means how much hydrogen peroxide remains at time t? We're only going to have 1% of our original hydrogen peroxide remain, right? The hydrogen peroxide times 0. And the original hydrogen peroxide is just H2O2 at time 0, so that cancels out.
Should that be the 0.00?
Oh, yeah. Sorry. This is 99%. This would be 99.9. Thanks. And so we just divide this by 0.00733. There should be a negative sign there. Seconds to minus 1. So how long will it take? 9,000 seconds?
417.
9,417 seconds. And so this is a typical problem that you can do. First order kinetics. One of the times is very important in first order kinetics. And that is the half-life, you know. In first order kinetics, T1/2 is important. The reason T1/2 is important in first order kinetics is because T1/2 is a constant, you know. And so when we're looking at reactions, how do we characterize reactions? Usually what we want to know about a reaction is what is its K, you know, what is its rate constant. The bigger the rate constant, the faster or the slower the reaction, the faster the reaction. So big rate constant means fast reactions. But, you know, if you're given a K like this, 0.0000733 seconds to the minus 1, it's hard to visualize that, right? It's pretty hard to visualize it. And so for one convenient thing to do for first order reactions is rather than characterize them in terms of K, we characterize them in terms of T1/2. T1/2. And so let's answer the same question. How long would it take 50% to decompose? 50% to decompose is T1/2, right? And so what we'll do is we'll take ln, we're going to have 1/2 of our original over our original is equal to minus kT. And therefore the T is equal to the ln of 1/2. The ln of 1/2 is negative 0.693 times the negative gives us positive 0.693. So it's 0.693 over K. And so this is an important equation to switch between K and T1/2 in first order kinetics. And so let's do that for the hydrogen peroxide. T1/2 here for the hydrogen peroxide is going to equal 0.693 divided by K, which is 0.0000733 seconds to the minus 1, which means the half-life of hydrogen peroxide is 9.5 seconds? 945 seconds? All right, so that's constant. So every 945 seconds, we should lose half. But, you know, T1/2 is not so useful for zero order and second order. Why? Because it depends on concentration. If we do the same thing for 0, let's say at time t we want 1/2 the original is equal to minus kt plus the original. And so we'll subtract 1/2 of the original from both sides and add kt to both sides. So we'll get 1/2 the original. And so T1/2 is equal to 1/2 the original concentration, the starting concentration, divided by K. And so what happens is your T1/2 depends on what your starting concentration is. It's not a constant. It's going to change as the concentration changes. And it's going to be, each successive half-life will be 1/2 the previous one. If we do the same equation for second order, we'd see that each successive half-life is double the previous one because it depends on 2 times the concentration rather than 1/2 of the concentration. And so those patterns hold that we were talking about earlier mathematically. So I wanted to finish that problem and talk about practical point of data. We collected a lot of data for your kinetics. So it should minimize the amount of random error that we see. And tomorrow, I think at the beginning of the lab, I'll talk about the kinetics lab that we just did. Calculations for that. All right, today I want to talk, when we have multiple reactants, the rate for this is equal to Ka to the m, B to the n, C to the O, however many reactants we have. And so there, experimentally, how can we figure out what M, N, and O are here? We could do pseudo M, pseudo N, pseudo O. That's one option. Is there another option? Another option is we could do the method of initial rates. This is something we did in the lab yesterday. Do you know experiment 2? We kept one of them constant. We kept the CV constant, so the initial concentration didn't change. And we doubled the hydroxide. And therefore, if the CV concentration is the same in experiment 1 and experiment 2, then that has no influence on the rate. And what has the influence on the rate is doubling the hydroxide. And so the method of initial rates, we could do, the same thing. What we do is we set up a table, where we double A and keep B and C constant. That way it allows us to figure out the dependence on A. We double B and keep A and C constant, right? Initially, they're going to change over the course of the reaction. And so this is the method of initial rates. The method of initial rates is discussed at the beginning of the chapter, but I waited until later to really talk about it. But it's not too difficult to do. You just take ratios to see how the rates change. We'll look at the examples in there. So we could use the method of initial rates, but method of initial rates and pseudo, both of those are experimental methods. How can we derive M and N theoretically? What does M and N and O, what do these depend on theoretically? In other words, what do these mean and where do they come from? And so the second half of this chapter is devoted to talking about M and an O, you know, what they mean and where they come from. They come from what we call the mechanism for the reaction. They don't come from the coefficients here, A, B, and C. Not necessarily from the coefficients A, B, C. Although they might, you know, they might come from the coefficient. And so is it possible to come up with a theoretical derivation of K? Where does K come from? Typically it comes from experiment, right? You got a K 000733 or something like that. There's a number you pull out from the slope, one of the graphs. But the same thing, you know, where does it come from? You know? And you know, the bigger the K, the faster the reaction. And so K comes from collision. Let's just say, you know, this theory. Collision. In other words, K comes from our understanding of how things collide. And then we can derive these things. This is all part of this mechanism, you know. The mechanism. So if we know the mechanism, you know, and we know something about the collisions, then we can calculate or predict what K is, what M is, what N and O are. You know. And so let's take a look at what looks like a simple reaction. Let's look at this. I'll talk in more detail about this in a minute, but if I have one methane plus two oxygens, this goes to CO2 plus H2O liquid. Gases except H2O. I know that the rate is going to equal K times the methane concentration to the M and the O2 concentration to N. If I think in terms of collisions, right? Just think in terms of a collision between methane and O2. I got a bunch of methane in here, and a bunch of O2 in here. Methane and O2 collide, right? Now tell me, if I double the amount of methane, what happens to the number of collisions? Does the number of collisions stay the same, decrease, or increase? Increase. And so if I double the amount of methane, how should the number of collisions increase? Should it increase by a factor of 2? Or if I double the amount of methane, do I get twice as many collisions? 4 times as many collisions? Half as many collisions? How many extra collisions? Well, let's think not in terms of O2, but let's think in terms of a brick wall. If I have a brick wall here, now, if I double the amount of methane, what did I just do to the number of collisions? I just doubled the number of collisions. Is that right? This linear thinking, or should I go non-linear? In other words, if you doubled the moles of O2 or methane, actually I'm not talking about methane, if you double the moles of methane in a sealed container, what happens to the pressure? Does the pressure double? Does it quadruple? Or does it go up by half? Or some nonlinear factor? I'm talking for an ideal gas. Yeah, if you double the number of moles, you're going to double the pressure, right? That only makes sense. And so based on our understanding of gases, and methane we're going to assume is behaving pretty ideally, if we double this, it should, you're probably thinking about real gases, you know, and other effects that come in. But let's just think in terms of ideal. In terms of ideal, we should double it. And so if we double the concentration of methane, the rate should double, meaning m should be 1. It should be first order because it didn't quadruple and it didn't go square root or anything like that. It just doubled, right? Likewise, this. If I double the O2, right, the rate should increase too. In fact, this is a tricky reaction because this reaction requires not just one O2, but this reaction requires two O2s. And so the way one can visualize that is like this. The way I can visualize this is, let's imagine methane's in the center here, and I have an O2. I'll call this the left O2. And then I have an O2 over here. This is the right O2. And so now I got a collision here. I double the oxygen. When I double the oxygen, can I just double the left oxygen? No, I have to double all the oxygen, which means I'm doubling the left oxygen and the right oxygen. And so if I double the left oxygen, that should double the number of collisions. If I double the right oxygen, it should double the number of collisions, and the net effect is quadruple. And so thinking about just simple collisions, and just, you know, basic physics or something like that, we would say that the rate should equal K times the methane to the first and O2 to the second. And that's just the coefficients here, right? It just seems to make sense that in terms of a reaction, and reactions are just these collisions, that should be true. Right? Yes. Right. But, there's all of that but, think about this. Does this reaction occur because what has to happen is you have these gases, and O2 is moving very fast. How fast is O2 moving? Pretty fast, like what? 500 meters per second or something like that?
Room temperature.
A room temperature? You know, which is a huge number of miles per hour. It's moving fast, right? And so if you have a reaction between methane and O2, what has to happen is the methane's moving, let's say the methane's moving this way, right? That means two O2s have to synchronize their collision. How probable is this synchronized collision? Because if one O2 hits it and the other misses it, we don't get reaction, right? And so what we need to do is it has to be perfectly timed. The methane comes here and then sandwiched, right? Every reaction has to be like that. Is that likely to occur? No. And so this is what the mechanism is. We call this the net reaction. The net reaction isn't necessarily how it reacts. Hidden in the net reaction is the mechanism. And so in the combustion of methane is not a simple collision like this. If it were a simple collision like this, then this would be the rate law. we call it a simple collision because that's the collision there. Actually, when methane reacts with O2, the exact mechanism, that is, when you look at a flame, let me just finish. When you look at a flame, what is the blue stuff? You see? What is that blue stuff? Is that CO2? No, blue's got to be water. Water is blue, isn't it? So the blue that you see there is water. Is that right? No, it's not water. So what is that blue stuff? Why is it blue? Because methane's colorless, O2's colorless, CO2's colorless, and water's colorless, right? So, that gives you your first clue that there's something going on in there that you don't know, right? And that something going on in there is there are a lot of other species in there because the total mechanism, it turns out that, I don't know, just recently, maybe about 10 years ago, somebody figured out all the possible collisions in a methane-oxygen flame. And it turned out that there were, I think, over 2,000 different collisions that can occur in there, producing different species. And so when we see a reaction like this is the overall reaction, the beginning and the end. But what happens in between, there are a whole bunch of branches in here doing different things, right? And one of these pathways is going to dictate the kinetics, and we'll talk about that later. I don't have your exam. Sorry, I'll get your exam at the beginning of class tomorrow, but I have your quiz from before. So if you want to take this, let me tell you about this quiz. Do you know how to solve this? No. Because you have the Ka, the Kb, and the Kw, you have to solve them simultaneously. You can't solve them stepwise or individually. And so that's what I was looking for. All right, Omar, Arthur, Mauricio, Matthew, Marco, Jose A. Marco, Jose A. Adam P. Ariana, Rocio, Jose Q. Timothy, Sydney, Angie, Stephanie, Cecilia, Rama, this is yours. Oh no, that's yours. This is yours. Rama, Natalie, Dustin, Na.
You gave me the wrong one.
Tyler, Jessica, Alex G.
That's Sydney's.
Kone,
And this is yours.
Sandra,
Yeah.
Angel, Gina, Amanda, Keith, Matt, Adrian,
I have a question.
Yeah.
You're done.
Question, Professor. For this one, what is the calculation which is a higher solubility? What kind of calculation is
S,
it?
you calculate S.
Just
S from the ice table.
okay.
Starting off
Other
with
question.
0 and
Didn't
0.
you say you were going to let us finish that quiz last time? You said you were going to give us like more time or something, and we turned it down.
Oh.
So otherwise.
All right. Well, let me think about it. Yeah, if I said that, then I'll give you more time first.
Okay, so my question is, here, I don't know why I'm getting confused since I'm getting figures between these two. So here, what I'm thinking is, because I know there was one that you counted decimals or something like that, but I'm not.
Don't round it, right? Why are you rounding that?
Where? Oh, where?
3.00.
Oh, it was given like that.
Oh, is it?
Because it was given as a pH, so I'm getting the concentration
Oh,
of
okay.
hydronium. But then I'm getting confused with the significant figures. Like
This
here-
is 2 sig figs.
Why is it 2?
Because this is a concentration or the K or something like this. This would be the power function here, so you need 2 decimals.
2 decimals.
This has 2 decimals, it's a power function, therefore this should have 2 sig figs. Here.
So this one would have 2 sig figs, which
Yeah.
can be like 2.11, but then 2.1. But then this one, if I have like 3.050, then it would be 2 decimals.
Yes, 2 decimals.
So the number, like the actual number in front doesn't count. It's 2
Yeah,
decimals
right,
that count.
right. It's decimals.
So, with calcium